Hey everybody, we're going to do a quick video lesson so I can help you through one of the assignments that we have today, the calculating the relative humidity, the math practice. But before we get to the math part of it, we just kind of need to look at the temperature and moisture and how that affects air. And since we've been doing all kinds of things with air and meteorology and weather, we know that temperature and moisture in the atmosphere makes a major difference in our weather, climate, everything else. So think about what we've talked about with the atmosphere. It's composed of, and if you remember, no one at court wins, meaning nitrogen, oxygen, argon, carbon dioxide, and water vapor. So we're looking at the different temperatures and moisture. So we're looking at water vapor that's in the air. Well, we know that water vapor, if you heat that up, water is going to turn to a gas. If you cool it off, it's going to turn back into water, or it's going to turn into a solid like sleet, snow, hail. So the temperatures are going to definitely make a difference. So let's kind of take a look at moisture in our air. All right, so moisture in our air is the humidity, the amount of water vapor in the air. This was in your notes from Monday. And so think about those times that you have heard somebody say in the southeast and everything else, oh, what a muggy day it is, what a humid day it is, that you walk outside and you feel like you have a wet blanket that has just, a warm wet blanket that has just been thrown on you. And that's the humidity. It's the amount of water vapor that's in the air. Well, what we're going to be doing is we're going to be calculating the relative humidity that's in the air, so we can kind of begin to get an idea of what to look for and how we can know what our weather's going to be what our weather's going to be like when we can hear about the relative humidity that the weatherman talks about. Oops. So our relative humidity is the ratio of the air's actual water vapor content compared with the amount of water vapor air can hold at that temperature and pressure. So couple things to keep in mind here. It's going to be different all over the globe. If you're at the higher latitudes and you're up in 60 degrees latitude, 90 degrees latitude, you're going to be closer to the poles in either the northern or southern hemisphere. So you would have cooler temperatures. The closer you are to the equator, the more warmer it's going to be. So, the more the northern parts of our country are going to be cooler, the more southern parts are going to be warmer. They're closer to the equator. So we can look at the different relative humidity that's there. One of the things that you also need to kind of keep in mind is that warm air can hold a lot more water than cold air can. So warm air can hold a lot more water than cold air. So if somebody says that the relative humidity is 100% outside and you walk outside and it doesn't feel muggy and it doesn't feel sticky and everything else, you kind of have to think about what's the temperature outside. If the temperature is 40 degrees and it's cool and we have a relative humidity that is going to be 100%, that means there's about 40 degrees of wet outside as well as 40 degrees of dry outside. So that's going to be 100%. If you have a much warmer temperature and you have a difference in the humidity or how much moisture is in the air, then you're going to have a different relative humidity. So depending on the temperature is going to make a difference in that as well. But just keeping in mind that warm air can hold more water than cold air. And what I mean by that is if you think about what we know about molecules, if this was air, the molecules of cold air are going to be closer together. They're going to move a little bit less. They're going to be more condensed. That's why we say that cold air is more dense and it sinks and causes more pressure compared to warm air that is less dense, rises, and has a low pressure. So look at the space here when you have it. Look at the space that water can get in here. There's not as much space. Look at all the space in here that water can get into in between these air molecules. Okay, air molecules, lots of water can be held in here. Cold air water molecules, not as much water can be held in here. So we're going to have less water in the cold air than we are in the warm air, that possibility of being able to hold it. Okay, so now I'm going to flip this around and say, okay, let's say this is that, we got molecules of water in warm air. All these little red, or these little blue dots and everything else in here is the amount of water that is in the warm air. So the molecules are spread out, the water is spread out, and if it's warm, you know that water is going to be a gas. Then if you jump over here, the same number, if I counted this and I counted this, and there were the same number of dots, the same water molecules in cold air, that water is going to condense. It's going to come together just like the air molecules are. And if the air is colder, then it's going to start turning those water molecules into a liquid. So we're either going to get some rain droplets, or we're going to have dew that will form on the grass, or we will even have fog. Things like that. We'll have fog with those colder temperatures. Because if you think about it, when do you normally see fog? Early in the morning, and the temperature starts to warm up and the fog starts to dissipate. That's because all that condensed water droplets that are in the air making the fog, making those low-lying clouds called fog, are condensed, and they're more of a liquid base. And when it starts to warm up, they turn more into a gas, and they start to spread out, and it looks like the fog is dissipating or disappearing. Okay, so when thinking about calculating this, we need to come up with it. We'd have instruments, and if we were at school, we would be looking at temperatures with wet bulb and dry bulb thermometers. I don't have a hygrometer. I would sure love to get one day. But a hygrometer is, back up. The hygrometer is a way that you can actually measure the humidity in the air. That's what a hygrometer does. It measures the humidity in the air. Now, a psychrometer is a very specialized hygrometer. It has two thermometers here. One is a dry bulb, what's called a dry bulb. That looks just like a really normal thermometer that we have always used, the same ones we have in the classroom. And they will do, dry bulb can just get the present air temperature. So if you're thinking about air temperature, it's the same as dry bulb. Wet bulb is going to be something, it's going to have a thermometer that has a wick on it. It has a piece of cloth on it, and that piece of cloth will actually collect moisture. And so you'll get a temperature of that moisture that's in the air. So you're looking at the temperature of the air itself, and then you're looking at the temperature of the moisture in the air. So we're going to find the relative humidity, and we're going to be looking at dry bulb temperatures and wet bulb temperatures. Okay. So here's a chart that you have on your activity sheet and everything else that I gave you. So what I want you to do is, if you haven't already, save yourself some time. Excuse me. Stop the video. Sorry for yawning. Stop the video and either print out the file that I gave you that is about calculating relative humidity, and it says math practice. And at the top of the paper, if you printed it out, it says relative humidity. If you aren't printing it out and you're just going to use it as an electronic file and put your answers in there, you can go ahead and pull that up and have it in your Earth and Environmental Science folder, and you can kind of do a split screen where you have the video on one side and then you can type on the other side, so that you can kind of follow along with what we're doing. So stop the video right here and kind of get yourself ready to be looking at our file. Okay, so you have the paper that says relative humidity at the top, and it says write the steps to calculate relative humidity. So we're looking here, and the first thing we want to do is we want to make sure that we subtract the wet bulb temperature from the dry bulb temperature to find the difference. Okay, so remember wet bulb and then dry bulb. Dry bulb is the air, it's going to be your air temperature. Okay, so you're subtracting. If I take it and do it in math, I'm going to say, okay, what's the dry bulb minus the wet bulb, and then I'll get my difference, okay? Then you're going to locate the dry bulb temperature on the chart. So make sure you write down step number 2, locate the dry bulb temperature on the chart. And I'll walk you through how to do this. All right, step number 3, we're writing these down. If you need to pause, pause. But step number 3, locate the different wet bulb and dry bulb temperatures. Locate the difference wet bulb and dry bulb temperature on the chart. That's going to be on the chart. And then 4, go across to the right of the wet bulb and down from the difference to locate the relative humidity. And that's going to be in a percent. So we want to make sure we have that in a percentage. Okay? So, okay. So, here's where you have your paper, and you wrote that at the very top. So we're looking at the doing the math. So we're going to subtract the wet bulb. Now remember, here's the wet bulb right here. And then we'll subtract that from the dry bulb. And over here is the dry bulb. Okay. So if I take a look at this and I say, okay, subtract the wet bulb from the dry bulb. So 6 minus, we're going to subtract here. 6 minus 2, what's 6 minus 2? Pretty simple. That's going to be a 4. So we have 6 minus 2 is 4. Then I come to my chart here. Slide that up a little bit so you can still see. But we're looking at, this is where we talk about where you say you go down from the dry bulb. So I'm going to come down from the dry bulb. Here's my dry bulb temperature. So I'm going to come down from the dry bulb temperature and I find 6. I find 6 right here. Not the 2, the 6. Okay. Dry bulb temperature was 6. The wet bulb was 2. Wet bulb depression was 4. That was the difference. Here's our difference. Okay. So here my difference was 4. So 4. So if I come down 4, come down here and go over, there's my answer, 46. So that's going to be 46%. Okay, so that's a basic way of calculating the relative humidity with a dry bulb and wet bulb. When you get down lower in the chart and you hit number 9, 10 through 13, it's a little bit different. You'll have to do a little creative thinking and problem solving to try and figure out, okay, how do I find out what the air temperature and the wet bulb temperature are? So this is finding out the humidity, how much relative humidity is in the air, how muggy it'll be, how foggy it'll be, and always remember that it depends on the temperature and the moisture. If you have any questions, send me a text or ask any kind of questions. Let me know what you need, and I look forward to seeing you guys. Everybody stay safe.